Hello viewers. In the previous tutorial, we tried to know the basics of time series. In this tutorial, we will try to know what is ARIMA model, that is autoregressive integrated moving average models, and how to build it in R. So before building the ARIMA model in R programming, we should know some transformation. One of the most important transformation is Box-Cox transformation. So what is the motivation of Box-Cox transformation? A Box-Cox transformation is a transformation of non-normal dependent variables into a normal shape. Normality is an important assumption for many statistical techniques. If your data isn't normal, applying a Box-Cox transformation means that you are able to run a broader number of tests. The Box-Cox transformation is named after statisticians George Box and Sir David Cox, who collaborated on a 1964 paper and developed the technique. The motivation of Box-Cox transformation is that it makes the time series stable. What is stable? In our previous tutorial, we know that if our data non-stationary, if the mean and variance is not constant over time, if it changes, then we consider the series is non-stationary and it's unstable. So what does Box-Cox transformation do? The Box-Cox transformation make the time series data stable and the non-normal data to normal. Now all the core of the Box-Cox transformation is an exponent lambda which varies from -5 to +5. All values of lambda are considered and the optimal value of your data is selected. The optimal value is the one which results in the best approximation of a normal distribution curve. The transformation of y, that means dependent variable, has the following form. What is the form? The form is that y of lambda is equal to y to the power lambda minus 1 divided by lambda. If the lambda is not equal to 0, but if lambda is equal to 0, then it will be log y. That means the lambda is the power of the transformation. So let us take a look on the picture. Here the x-axis shows the times weeks and the y-axis shows the number of cases, COVID-19 cases. So the above figure shows the original data set of the COVID-19 data daily cases, and the below shows the Box-Cox transformed of the COVID-19 dataset. So the above picture shows that the data is not smooth or neither smooth nor stable, but the Box-Cox transformation shows that it's smooth than the trained data, that means original data set. Now the autoregressive integrated moving average ARIMA model. The autoregressive integrated moving average model introduced by Box and Jenkins 1990 is widely used for predicting time series data because of its capacity to handle non-stationary data. It is one of the most often used time series model in a variety of sectors of data analysis because it accounts for changing trends, periodic variations, and random disturbance in the data. It utilized for forecasting and better interpreting the data. An ARIMA model, ARIMA PDQ, where PDQ are the parameters of ARIMA model. The PDQ, where PDQ are the parameters of the ARIMA model. It combines the autoregressive order ARP and moving average order MEQ models with I standing for integration, where P denotes the autoregressive order, Q denotes the moving average order, and D is the differencing order. The difference order is used to make the non-stationary time series to stationary. An ARMA PQ model without differencing, it means it's already stationary. So an ARMA PQ model combines ARP and MEQ models, which is best suited to univariate time series analysis. The ARP model assumes that a variable's future value is determined by a linear combination of P previous observation with a random error term. The ARP model is represented mathematically as follows. That is, yt is equal to c plus phi 1 yt minus 1 plus phi 2 yt minus 2 up to phi p yt minus p plus a random error term epsilon t. So here yt t time observation, then c is a constant here, then phi 1 phi 2 up to phi p is the parameter of this model, and yt minus 1 year prior or 1 month, that whatever, either our time series is monthly, daily or yearly. If it's monthly, then 1 month earlier. If it's daily, then 1 day earlier. If it's yearly, then 1 year earlier. Okay, now the unlike the autoregressive order ARP model, the moving average model includes the independent variables for previous errors. Following the MEQ model, we can write the function here. Yt is equal to mu plus theta 1 epsilon t minus 1, theta 2 epsilon t minus 2, theta 3 epsilon t minus 3 up to theta, it will be theta q, sorry for the mistake, theta q epsilon t minus q plus epsilon t. So here mu is the constant, mu is the series mean, theta 1, theta 2 up to theta q are the parameters of the moving average model. So we can write the ARMA model ARMA PQ as follows. Yt is equal to c plus mu phi 1 yt minus 1 phi 2 yt minus 2 up to phi p yt minus p, and then the moving average model mu plus theta 1 epsilon t minus 1 theta 2 epsilon t minus 2 up to theta q epsilon t minus q plus epsilon t. So ARMA PQ model is nothing but the combination of autoregressive and moving average model. So based on the above discussion, if we take integration or difference operator to make the time series stationary, then the ARIMA model ARIMA PDQ can be written in the following form: y trans y prime t, here prime indicates fast difference. It means without fast difference the series is non-stationary, but after taking fast difference the series is stationary. So that's all about autoregressive integrated moving average model ARIMA model. Now let us practice it in R. Practice the ARIMA model in our program. So first of all, we will load our data here. So we write data. Our data is in CSV format. So we write the command read.csv file.choose header is equal to true. Okay, if we run this code, so it will take us to the directory, and I saved my data to the desktop file. So I will go to the desktop and select the data. My data name is data. So where, so this is the data. Open. Okay, so the data is loaded. Now we want to view the data. So PIEW view data. Okay, run it. Okay. So this is the data. This is COVID-19 cases data in Bangladesh. This is a daily data. It started from 1st April 2020 to 30 June 2020. So this is the daily data. It contains daily cases and dates data. So we will try to build ARIMA model using the cases data. So let us load some libraries here. So library forecast load here. So another library ggplot, t-series and lm test. This also should be loaded. If you don't have these libraries, then you have to install it using install.packages, then the library name, or you can go to tools, then install packages, then write the package name here. Okay, so since I have already installed it in my computer, so I'm not going to install it in my computer. So now we have to make the time series data of cases as time series format. So using the T series package, we will make the daily cases data as time series format. So we write dts function, then ts, then write data $, we select the cases, then we write strt start. It start, we don't need to start also because it is in date format. So we just write frequency here, frequency. So if we write frequency, and frequency is 1, since it is daily data, so we can write the frequency 1. If it's monthly data, then we can write 12, or yearly, then we also write it 1, or if it has, if the data was in quarterly data, then we can write it 4, or if it had weekly data, then we can write 52 or 52.5 or etc. So since it's daily data, so we write the frequency 1, and after that we run this code. So okay, the data took it as a ts format. Now if we want to check either the data is in ts format or not, we just write acad head function and write tts. Okay, run it. Okay, so the data is in time series format. So here shows that start 1 and 6. And because why it start 1 and 6, because we write the head function, and head function will let you to see only 6 observation of the data. So here only 6 observation, 1 2 3 4 5 6. That's why it shows end is equal to 6, but we actually have 91 observations. So it is now in time series format. So first of all, we will apply the Box-Cox transformation we just learned few times ago. First of all, we will find out the value of the lambda parameter of Box-Cox transformation. So we'll write here lambda, and then we will write the function Box-Cox. Okay, Box-Cox dot lambda, this function, and write our time series format data dts. Okay, so we run this code. Okay, very good, the code is run. Now we want to see the value of lambda, so we again write lambda and run it. Okay, the lambda is 0.260. So using 0.260, we have to make the transformation of this data. So now we will transform Box-Cox transformation. So dts underscore bc, and write the command Box-Cox, and the original data time series format dts, and include the lambda parameter value. So we will write lamb lambda is equal to lambda is equal to, we write lambda. Okay, so run it. Okay, so the code runs well, very good. Now what we will do, we will compare the original series and the Box-Cox transform series in one plot. So we will column bind the data and plot it. So what can we do, we will plot is, write plot, then we will write column bind C bind, then we will write column bind, then we will write our original data DTS, then our Box-Cox transform data, that is DTS BC. Okay, after that we will write here X lab, X exists level, that is year, or we can show as day, because since it's our daily data and we have to keep it in quotation. So okay, so if we run this code, oh very good, so you can see here this shows the comparison of original series and Box-Cox transform series. So the DTS this is original series, and it shows the time series is not smooth and it is fluctuating great, and it shows a gate pattern here, so the mean variance are not constant here, but the Box-Cox transformation shows the smooth of this data, but it fails to completely smooth the data and makes it fail to make the data stationary. So but it makes the data more normal. Now first of all, we will plot our original data in a time series plot to see the pattern of the data. Although we are seeing the pattern of the data in our Box-Cox plot here, but we will see in time series plot using auto plot function from ggplot to package. So we'll write auto plot and run the DTS original data set and run it. Okay, very good. So this is our original data and this is the pattern of the data. This is increasing data. It shows a linear pattern, as we can see. So now we will make the data stationary using difference operator. So we will make difference, we will take difference to make the data stationary, because the data is not stationary. So we will check is the data stationary or not using the augmented Dickey-Fowler test we learned in our previous tutorial. So first of all, check whether data is stationary or not. Although we are seeing that this is non-stationary, but we will ensure that this is non-stationary using the ADF test. So we'll write ADF dot test, then write the original data DTS, and we can indicate the lag is 1 because this is daily data, so we can use lag k is equal to 1 and run it. Okay, very good. The Dickey-Fowler test shows that the Dickey-Fowler test value is minus 3.0813 and the p-value is 0. Here the p-value is 0.1308, which is less than 0.05. So we cannot reject the null hypothesis, because it's the null hypothesis of the augmented Dickey-Fowler test stated that the data is not stationary, and the alternative hypothesis stated that the data is stationary. Since this p-value is greater than 0.05, so this data is not stationary and we have to take difference. So we will make difference of the time series data. So we'll write d1 for fast differencing and write di double f, then write the original data DTS and write di double f variance difference is equal to 1. We will try to see if the fast difference can make the data stationary or not. So run this code. Okay, it's now fast difference. Now we will test the ADF test again to check if the data is now stationary or not. So we will write d1 now and lag is equal to 1. So run this code. Okay, very good. So now the augmented Dickey-Fowler test shows the value minus 9.1516, lag order 1 and p-value 0.01. And here warning message shows that p-value is smaller than the printed value. So Now we can reject the null hypothesis and accept the alternative is that the data is stationary now. So for building the ARIMA model, we found the difference parameter d. The value of difference parameter d is equal to 1. We learned the ACF autocorrelation function and partial autocorrelation function plot. So using the autocorrelation function plot, we will determine the moving average order q and the partial autocorrelation function for determining the order of autoregressive order p. So we will write ACF of d1 first difference and run it. Very good. This is the ACF plot, and based on our learning on the previous tutorial, we learned that at lag 0 it has the highest value, that is 1. Okay, very good. So ACF diagram, there is an evident spike at lag 1, indicate that the moving average order q may become 1 because this indicates this cross the significance bound compared to the other slag. So we can decide the moving average order q is equal to 1. Now we will plot the partial autocorrelation plot function plot. So at PACF, then write d1 and run it. Okay, so this is the PACF diagram. So in the PACF, we can see that there is an evident spike at lag 0, indicates that the autoregressive order P may become 0. So we can take the autoregressive order P, the value of P is equal to 0. So now, and this function creates all possible ARIMA model and list all the models, ARIMA models, and give you the best model based on the AICC value. That means Akaiki's information criteria. So we use the auto ARIMA function and write our original data DTS and write trace is equal to true, so that we can see the all possible ARIMA models built from the auto.arima function. Okay, so if we run this code, so control, okay, so we run this code and we see here these are all possible models that are created from the auto ARIMA function, and we can see here that the optimum model is ARIMA 0, ARIMA 011. Okay, with drift. Why the drift is here? This drift indicates that since our original data is a linear trend and it is increasing pattern, so it is increasing positively day by day. So this is the drift, and the drift parameter is always positive, the positive value 43.5287. So it drifts positively upward. Okay, so our optimum and best selected ARIMA model is 011 with drift. 011 with drift because it shows lowest AICC value, that is 1243.936, and this is the lowest value among these AICC values. So our optimum model is ARIMA 011 with drift, and this one indicates that our data was non-stationary and we use fast differencing to make the data stationary. Now we can check the coefficient of our data, either they are significant or not. So we can write coef test using the ALM test library and write our ARIMA model. So we didn't write anything, so we can copy it and then paste here. Okay, now run. So this is the coefficient of our models, and we have the moving average order 1, and since the autoregressive order p is equal to 0, so it is absent here. And the moving average order, this is the only parameter here our in our ARIMA model, and it is significant, and the dip parameter is also significant, so our ARIMA model proves significant. So what can I do? We can do one thing so that our model, ARIMA model, is significant or not. We can check the residuals of our model. So we can write check residuals using forecast package and write our model. So this is our model and run this. Okay, so we found the residual plot. Wait, this is our transform data. This is save and the histogram of the residual plot. This shows our ARIMA model proved significant. So now we will try to forecast using our ARIMA model. So it's better to write something here because uh, copying frequently this code is not good. So we will write the code of creating model is m. Okay, so run it. Okay, so now m indicates the ARIMA model, our ARIMA model. So now we will make forecast of next 30 days. So what can we do? We will write forecast. So we will write f c forecast. So we will write forecast. This is the code forecast to forecast predict. Okay, now we'll write our model first m, then write h is equal to 30, next 30 days, for next 30 days, then run. Okay, now if we want to see our forecast data, so we can write fc here and then right click. Okay, so this is our forecast data. This shows our point forecast. We have 91 days data and it started from 92 to 121, 30 days data. So this is the point forecast. It is 80% lower confidence value. This is higher value of 80% confidence interval. This is 95% lower and 95% higher value. So this is our forecast. So if we want to see our forecast data in a plot, so what can we do here? We just write auto plot and forecast, auto plot and write fc. Then what can we see? So this is our forecasted data. So our forecasted data also suggests that this is an increasing trend. So in future the cases will be increased. So this is all about ARIMA model. Thanks for watching.